We got a little stuck in between a section or inside a section that was on modal truncation. I had introduced the basic concept. First I had introduced the basic concept of model reduction via projection. I had shown that projection in a way naturally leads to interpolation of the reduced order model at certain points. In case you choose your projection matrices in a particular way. We will come back to this issue later on in this lecture today. And then I gave you a first example for a model reduction method that is based on projecting the model onto a subspace along a complementary subspace. So actually I didn't say that yesterday, but if you're familiar with finite element methods or Ritzka-Jokien procedures or something like that, these are test and trial spaces, sometimes called in that world, and sometimes it's also used in model reduction. Anyway, so the particular choice of trial and test spaces we took here are the subspaces spanned by certain left and right eigenvectors of the matrix A, where we have to select R eigenvalues that are of our interest. And as I mentioned yesterday, one of the tricky issues, or one of the issues in that method, is how to select. So you have to have a measure on deciding which are the eigenvalues that you want. And due to this diagonal structure, we came up with this error bound which gave us one selection criterion, namely to choose those eigenvalues in the reduced order model. I haven't said that, but of course the reduced order model, or the poles of the reduced order model, are a subset of the poles of the original model, because here in A hat, which we use as our reduced system state matrix, that A hat is just this diagonal with the eigenvalues lambda 1 through lambda r that we selected. So the subset of the eigenvalues of the original A and the reduced A coincide. That means the poles of the reduced order model are a subset of the poles of the original model. Okay, we choose those eigenvalues for our reduced order model that are closest to the imaginary axis, or that have the smallest real parts, assuming that the system is stable again. So otherwise the criterion would look different. Because that choice minimizes this expression over here, because you maximize the denominator here among all possible choices of R eigenvalues from the original N. As I said, also a repetition, the computation is an issue here. You usually cannot compute all eigenvectors, all eigenvalues and eigenvectors, because of the problem sizes. What you usually do is you compute a few thousand. And if you look at commercial packages like Nastra and ANSYS, they run the Lanczos process without any particular precaution of numerical stability and so on. They do, of course, a little orthogonalization, but they don't do any kind of fancy stuff. They just run it for a couple of thousand steps. And compute, so in that way, compute the smallest and largest eigenvalues of the model. The largest you can usually throw away in structural dynamics because they correspond to noise. But the smallest ones, or the smallest in magnitude usually also lead to the ones that are closest to the imaginary axis, and it's not always the case, but you can apply some shift technique to your matrix A. You have learned that probably in the eigenvalue course, that there's so-called shift and invert operators. Anyway, and then among these couple of thousand that you have computed, you apply your selection criteria. That means you have probably missed 100,000 others that you have not computed. And you just hope that among these 100,000 others that you have not computed, there are none that influence the dynamics of the system too much. And it works. Airplanes are flying, bridges are holding up most of the time. And it's used everywhere. You should be aware of that. Okay, it's probably still nowadays mostly used model reduction technique, although we are preaching to the engineers that there are more sound and reliable methods around nowadays. Okay, so this was the basic method, and it was the error bound. I had talked about this, and then I wanted to tell you a little bit about how it works and why it's a teaser that even though it looks bad, it does probably the job that you want. So if you look at the transfer function again in this Bode plot, I explained that yesterday also, you plot the magnitude of the transfer function with respect to the frequency, and you have this particular scaling, so the y-axis is printed in decibels, but that's just a scaling issue. And then you see that the transfer function in our original model has these peaks. I will come back to why there are these peaks in a second. And it's important from a structural dynamic point of view. The peaks have something to do with the excitation frequencies in your system. So if you want to have a reduced order model, you want to have these excitation frequencies in your model. And you want to match the transfer function around these peaks. And the interesting thing is that this works already. Oops, where's my MATLAB gone? Already for quite small numbers of R with this method, because it's focusing only on these peaks in a way. Because these peaks are induced usually by the eigenvalues closest to the imaginary axis, which we try to use in our reduced model. So here in this example, let me just, I loaded data from a benchmark example called Beam. I didn't look it up, unfortunately, but I think it's a beam that is fixed here at the wall and has a free tip here, and so you can investigate the behavior of the beam if you apply a force here to that side. So it's a very crude approximation. The system matrices are, as you can see here, A is only of size 348. We have only one input, so M is equal to 1, and one output, so Q is equal to 1. This benchmark is part of what is called the Slycott benchmark collection for model reduction that is freely available in the internet. You can download it from various websites nowadays. The one that we keep up is that thing we don't need anymore these days, Slycott.org. That's one way to get to the Slycott benchmark collection, and I think we'll tell you a little bit about other benchmark collections later on. there's also nowadays, we have a wiki running where you can find more information on examples. Anyway, that's the example. And now I apply this modal truncation method. And first I compute all the eigenvalues. In that case, it's only 348. That's just calling eigen. And I sorted the eigenvalues. They come out here. You see they are all stable. That's nice. These are only the real parts. So you see here the closest one to the imaginary axis is 0.005. So it's not too close. And you have two of them because these are all complex conjugate pairs of eigenvalues. So I just show the real parts here, and you see they are growing until you, oops. Let's do it again. So I showed you the eigenvalues, so we don't have to do that again. And here you see the transfer function printed in Planck and the first order model. And you can see that already with a reduced order model of order r equal to 1, you catch that peak up there. And it's because this peak is induced by this first eigenvalue, which is closest to the imaginary axis. And that's the one that we selected for our reduced order model. We keep the eigenvector in, so you're able to catch that peak. You see that it doesn't do anything in the other parts of the transfer function. So if you go to r equal to 2, nothing changes. Why is that? Because we have this complex conjugate pair of eigenvalues, and we just now the selection criterion is closest to the imaginary axis. I choose this complex conjugate partner, and that one only does help here. It does help a little bit to include both. So you get already a good matching here, this area. But it doesn't, you don't get any other peak, of course. Then you pick r equal to 3, the next one, and you get the next peak. You see here, that's okay. And then r equal to 4, you improve, but you don't get another peak. And that goes on with r equal to 5, you see, you don't get another peak. It's not always that the criterion we selected is the best one, as we will see after this example. So we have to continue a little bit. R equals 6 doesn't do anything again because it's a conjugate complex pair. R equal to 7, now we found, or we selected the eigenvalue that's responsible for that peak. So obviously the third eigenpair wasn't responsible for any of the peaks. Yeah? So although it was the third closest to the imaginary axis and by our selection criterion got selected, and if we had not selected it, our error bound would have been worse. For the model reduction, that didn't help any at all. And the reason is that you have the influence of B and C that we do ignore in our selection criteria. And then you can go through this. 8 doesn't change too much. 9, you get the next peak, and so on. And for r equal to 20, you do a fairly good job by catching the peaks up to this point, but you're still not here. And in a model that you would be happy with, usually you would at least try to get this peak into the model, because that's still on the level of 10 to the 0, meaning of order 1. and that you want. If you have say a peak in that area up here with a magnitude of larger than 10 or 100, and you have some small peaks around here at the level of 10 to the minus 5, most often you are not interested in matching them. They are usually not important for your design. But anything that's up here, you should catch. Okay, so this was the example. We have a similar exercise. No. We have a similar exercise with the Arnoldi method, I think, right? Yeah. So you can compare. This is easy to program as well, so if you like, you can compare to the Arnoldi method. Okay, let's go back to the talk. Where is it? All right, so what I just wanted to tell you is that its error bound is pretty lousy, as you can see here, right? Still, from the engineer's point of view, the approximation is not so bad. And getting this peak in, you wouldn't improve much on the error bound. But it's absolute error. So if you do the relative error, you divide the whole thing by 5. Well, you have to take the logarithm and then times 20. So this, what is this? Can somebody do the computation? I never can. So it's little. The relative error will be a little bit smaller because the H infinity norm of the system will be the value at this peak, basically. So that will be the H infinity norm. It's here at about 60, 70 decibels. All right, so this is model truncation. And I told you, yes?
So we actually we use one model to check another model. And it happens in a big model, we actually have some extra noise or some extra parameters that the smaller model actually reflects the relative vector of the bigger one. Oh, it's not always.
It's a.
I mean, can be actually the reduced model, the one that we are getting, can reflect the situation better?
Well, I mean in the methods that we have here, they can only use the information that you have in your high fidelity model. Okay? So we don't use any extra information. If your high fidelity model has noise, that will most likely also be present in the reduced order model. It
so
could be
those small oscillations, the small at the end the red line doesn't help or the blue.
Yeah.
It cannot happen. It's just like a mistake.
It's a question whether this is noise or this is still real dynamics. That's not so clear from the modeling point of view here. If that were a model of size 100,000, the finite element model, and you would look at the 90,000th peak, that would be noise. That's clear. And that you don't want to reproduce because it doesn't matter. And that you would not reproduce in a reduced order model. But the amount of noise around here, that's an information we don't have, basically. And usually the first 20, 30, 40, 50, 100 modes of a system, they are physically relevant. Well, I'm not a structural engineer, so you have to discuss with these people if you want to really get into this modeling aspect. But the first couple of thousand modes are usually physical, and the rest is modeling noise. Yeah. Okay, so I was dwelling upon this issue that just selecting the eigenvalues closest to the imaginary axis wouldn't give you the full information. And people have thought about other criteria. Oh, sorry, there are two issues I wanted to mention that I forgot that I wanted to mention it. So there's one thing. you usually want to have zero gain, steady state zero gain. That means you want to match the model at frequency zero. That's in particular important in structural mechanics. Here we are able to do that just by selecting the eigenvalues, but often you are not. So what people do is so-called base enrichment. So they attach, or they assume that we have run into stationary, in the stationary state of the system. That means that our time derivative becomes zero. And then you just apply, because loads can be anything, you apply unit loads from all possible directions. So you choose the as input functions, the unit vectors, j equal 1 to m, so as many as you have inputs. And then you solve for x of t, which then of course is a constant function, a inverse bj, minus a inverse bj. And you plug these vectors into your basis for projection. These are called static modes or static correction modes. And from the interpolation framework, we immediately see that we achieve what we want. We achieve g of 0 equal to g hat of 0, if we include that. Because that is just the property, so A inverse, that would be S0 identity minus A inverse times B. And we had proven already yesterday that if we include that in the subspace, we have interpolation. And S0 is 0 here, so that's why we have only minus A inverse. So we achieve interpolation at 0. That's what we wanted to have. Yeah? Now, of course, if you do base enrichment in the two-sided projection method, you also have to do something with the complementary subspace, and that gets a little tricky. In particular, if your number of inputs is not the same as the number of outputs. So the suggestion that is obvious from the interpolation framework is to include A transpose inverse times C transpose. Together with this condition, that gives us Hermite interpolation. I will give you the full theorem of that later, and we'll prove it in the afternoon, or maybe tomorrow, because we do practical exercises today. But, of course, maybe these are less or more vectors than we have up here. So you have to do something about that. And I'm not aware of any intelligent choices here. If you have less column or less outputs than inputs, that's good. Then you just add random vectors, orthogonalize them against what you have, and you're fine. Because you have all the properties, you cannot destroy them by adding some random vectors. If you have to delete vectors from, because C has more rows than B has columns, that means we have more outputs than inputs, you have to delete some of them. You will lose this full interpolation property here. That might be not so bad in the situation here, but you will not get that in full anymore. If you have to delete, what I would suggest is to use an SVD of this creature and select the M dominant singular vectors to include in the subspace. That will probably give you the best information. In which case you probably lose the full Hermite interpolation property, but probably you'll still get a better approximation than doing anything else. All right, this is one way to go. And then there's another technique that is around in structural dynamics, and this is Guyan reduction. And this is a model reduction itself. And it will show up at other situations as well later on. So in finite element world, what we sometimes do, or what people do, is if you have substructure, say you have just look at the gyroscope example that I introduced yesterday. So you have this bearing and two wings attached to it. Now if you do a finite element grid, yeah, whatever. And so on. I'm not a finite element guy, so I'm not good in painting this. I don't want to have hanging nodes. And so on, and so on. Okay, so let's say that's the grid on that wing, and then something similar here. Maybe different grid. For whatever reasons you have chosen it in this way. And then you also have a grid here. So you have your triangles and you have all these nodes. And say if you have an elastic problem, the deformations or the deflections in these nodes are your states. So what you can do is basically you do a sort of domain decomposition. I didn't paint that here right, so that should be. And the most important nodes in this picture are probably this one, this one, this one, and this one. Or you can actually make that one node if you want. Because all the information from that substructure passes to the other substructures through these nodes. These nodes are called master nodes. And the other ones here inside this part, they are the slaves. And then a typical idea in substructuring is this what is called static condensation or Guyan reduction, to reduce your model on a model which only has the master nodes and solve for the slaves. And this is done as in the following. You again make first this stationarity assumption. So you set the time derivative to 0. Then you solve the second equation for x2. And you plug it into the first equation, in the first part of the equation, and also in the output equation. And then you get, oops, I forgot the output equation here. Then you get a reduced order model where now you only have the master nodes in the model. The master nodes are usually much less than the slaves. So this was a simplified view of this issue. Learning about this itself would take a course. Well, that's a basic idea. And the basic principle that we will use later on also in combination with other model reduction techniques. Because you could also think of not putting the whole dynamics to 0, but only saying, okay, I have variables x1 and variables x2. The x1 variables develop slowly. The x2 variables develop very fast. They live on a different time scale. And then we just, as the simplest way of solving a multi-scale problem, we set the time derivative of x0 to 0, because in compared to x1, it reaches the stationary state very quickly. And then you get the same formulas. So this is say if you have a 2-scale problem with 2 time scales, you can do the same thing. All right. So these are two things that you can combine with modal truncation. You often do this after you have gone to this modal coordinate, so you have already reduced your system to diagonal form, but in the way that you use all the 1,000, 2,000, 3,000 modes that you have computed, and then you apply the technique before doing model reduction. And then you could, if you like, you can even further reduce that model. All right. Ooh, that wasn't intended. I'm not done with the course yet. Okay. So now we want to make a more intelligent choice of our modes in the modal truncation procedure. And for that we need what is called the pole residual form of a transfer function. Assume for simplicity that d is equal to 0. And then you can do a partial fraction expansion of your transfer function in the following form. And this is quite easy to show just using the eigendecomposition of A. So if A is diagonalizable, which we assume here, otherwise you would have higher order terms in the denominator, but let's assume for the moment that A is diagonalizable, then you can write it as x dx inverse. D is a diagonal matrix with the eigenvalues. X is the matrix of right eigenvectors, and x inverse has as its rows the left eigenvectors. And if you then plug the spectral decomposition of A into our transfer function, you see that you can pull out the right eigenvector matrix to the left and the left eigenvector matrix to the right. Yeah? You plug out the x inverse here, inverted becomes x, goes to the other side, x goes to the left, is inverted and goes to the other side, x inverse comes here, x inverse I called y. And then if you write it down in this, now in the form that you have up here, and multiply it out, you just get that formula. So this is what is called the pole residual form of the transfer function. And it's clear because in this formulation, the transfer function is described by its poles, which are the eigenvalues of A, lambda k, and the residues, Rk. Why are they residues? They are residues in the true sense of the residual theorem from complex analysis, which are defined as the limit of S going to lambda L of S minus lambda L times G of S. And if you plug in our formula for G of S, what remains is actually RL. So RL is actually the residual of G at lambda L. So in the numerator we have the residuals of the transfer function, and in the denominator the poles. That's why it's called pole residual form. Now we see that if we want to match the transfer function, the criterion to select the eigenvalues which are close to the imaginary axis is still not so bad, because terms for which the eigenvalues in the imaginary axis are close to the, in which the poles are close to the imaginary axis, become large on the imaginary axis. The denominator becomes small on the imaginary axis, 1 over the denominator becomes large. But then Rk kicks in. If Rk is small, it doesn't matter whether that pole is next to the imaginary axis. Assume there would be even an uncontrollable mode, that would mean that YKHB is 0. Or an unobservable mode, that would mean C times XK would be 0. Remember the Hautus test. Our residual would be 0. So no matter how close that eigenvalue, that pole would be to the imaginary axis, that term in the transfer function doesn't play a role. Yeah? So it's two things that play a role here. One is how close is the pole to the imaginary axis, and the other thing is how big is the residue. Yeah? Okay, so the criterion that one can think of now to select the modes in the modal truncation procedure is the norm of the residue, which if it's a single input, single output system, it's just a real number. It's just the absolute value of RK, otherwise it's, say, the spectral norm, divided by, again, the real part of the pole. So this is a new criterion that's a little more intelligent, because it now, you take in the influence of the C and the B. So to speak, it weighs the controllability and the observability of a pole and the associated state, the associated eigenvector in that criterion. Okay, and so you call those poles which have this, where these quantities are largest, the dominant poles, and these will have the most important influence on the input-output behavior of the system. That's what we expect. Okay, so here a student of mine came up with an example to illustrate this. And the transfer function here is not very exciting. It has not really developed peaks, because otherwise it's not so easy to plot. But it's wiggling around, so it's not good cannot be well approximated by a straight line or a parabola. You have to do some work. And now I don't know whether you can see that picture very well. So here we plot the transfer function only on the imaginary axis. Now that doesn't give us the full picture, of course, of the transfer function. The full picture is that we plot it on the left half plane. And then that's getting a little bit more excited. What we have just seen in the previous plot, that black line, you can see here. Actually, can one turn off the lights? Does anybody know? It's not much better. Is there other? Anyway, so you can see that black line. Here's the imaginary axis, or the upper half of the imaginary axis. Here that's much better, thanks. So here, that's the black line that we saw in the last bit. That's the transfer function evaluated on the imaginary axis. And then you see what a nice landscape our transfer function makes in the left half plane. And you see, of course, there are the poles, so you have singularities. That's what we want to see. Where are the singularities? And there are, for instance, poles like this one, which have small real part, and which is important. The bigger dots here are the dominant poles computed with that measure that I just introduced. But then the next one here, it's not important at all, because obviously B and C cancel the influence here. And then you see the next singularity, which is not it's cut off here, because you cannot, otherwise you couldn't see anything. So you have to see this goes up to infinity, of course, here. The next one is here, and then the next one is here. So you see, these are the selected dominant poles, and you miss 2 or 3 that you would otherwise select with the old criterion, which is only based on nearness to the imaginary axis. Okay, now what is the influence on model reduction? So here you see again the transfer function, but now you see the imaginary part of the selected dominant poles. They are here, 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 and here. And of course the complex conjugate partner. And if you choose these 46 of these dominant poles, that's what you have to do in that model, you get an exact matching. I mean, it's not exact, but in the eyeball norm, it's good of this function. So you have reduced from 217 to 46. This is not really impressive, but usually the number of important things going on are in that range between a couple of hundred, couple of thousands, and then if you go down to 46 and you have these 10,000 other modes that correspond to basically noise and you throw them away, then it's a quite good reduction. Okay, so this is what you see. Just to compare, that's the blue line here is what you would get with the old criterion, where you have done base enrichment by adding static modes to the model. So you don't do anything up to here. Here you that pole you get, and that, and also this one. So you see that with this dominant pole algorithm, or this dominant pole selection criterion, you do really better. Now the question is, how do you compute the dominant poles? Of course, what you can do is compute again the full eigendecomposition and evaluate the criterion. And that can be done again with many algorithms, and you can do it in the same way as in modal analysis. You just compute the first few thousand eigenvalues closest to the imaginary axis and apply the dominance measure just to them. But there are also variants of algorithms which you can steer to converge only to the dominant poles. So you don't have to first compute all the, say, 1,000, 2,000 eigenvalues next to the imaginary axis, then apply the criterion. You can, if you say you want to have 50 dominant poles, you can define algorithms that only compute those 50 poles. And there's the so-called subspace, or there was first a dominant pole algorithm, which is not converging very well. You can then accelerate it by using subspace iteration. Basically, this is a variant of the Rayleigh quotient iteration that you know from the symmetric eigenvalue problem. You can also do something similar for non-symmetric eigenvalue problems. It loses its cubic convergence, but still works okay. And then there's also something called the Jacobi-Davidson method that you can adopt to this special situation, and that's a recent paper coming out of my group. The work done here was mostly done by Joost Rommes from, at that time, from Delft University. He did the algorithm, and and Freitas and Martins, they work in the energy sector in Brazil, designing the energy network in Brazil, and they were interested in these methods, and they came up with this dominant pole algorithm first, but couldn't get it converged, and Rommes had experience from numerical linear algebra to make it work, so they joined forces. And then later on, we and also other people worked on variants of Rayleigh quotient iteration, subspace, the Jacobi-Davidson method to get this. I don't want to go into these algorithmic details, that gets quite technical. It's basically, you can also think of the methods as a special Newton method, which you steer to the right target, so to speak. Questions? Not? Okay. Yeah, I think let's go for 10. No, the usual break is at 11:10. No, okay. It's again jumping into a new topic, so we do a break a little bit earlier. So we do a 10-minute break and come back here at 11:15. We come back to this issue that projection has a relation to interpolation, and it also has relation to other ideas, which in the model reduction literature go all, well, show up in various areas. So the same methods show up in various areas under different names. Pade approximation is one of the things that we do, but we also do rational interpolation, and we also do moment matching, and this is all the same in this context. Okay, so we consider here, and this is a little bit change of the printout. The printed slides. I put in the E again just to show you that here we can deal with the E even if it's singular. You have to be a little bit careful there, but you can do it. So mathematically nothing changes compared to the printout where you only have the identity here. Okay, and we put the D equal to 0 again because that just is in the way of the presentation, and it doesn't play a major role. Just if there is a D, set the reduced D to the original D, and it's probably a good choice. What you can do if S0, which earlier on was S star, if S0 is not in the spectrum of A comma E, so we have to assume that this is a regular pencil, so you do not have the case that all complex numbers are eigenvalues in a sense for a singular pencil. So here you have, say, if E would be invertible, you still have n finite eigenvalues. If E is singular, you have maybe only n minus q or n minus k finite eigenvalues, but still natural number of finite eigenvalues. And you avoid them. So you pick some S0 that could be complex, that could be real, could be purely imaginary, whatever you like. And you rewrite your transfer function in this way. So I have only added S0E and subtracted it again. So there's nothing happened. And then you pull out the S0E minus A to the left, so that with the inversion it comes here. And because I pull it out to the left, I have to redo that here. So we have this expression. And I now use the abbreviation. I call this matrix A tilde in the following, and this matrix B tilde, to make the notation a little bit clearer. Okay, so that's what we have. So now something should come to your mind about the inversion of matrices in the form I plus another matrix. You certainly have seen it. It's the Neumann lemma. Special case also if you think of maybe of Taylor series expansion. Or you could also talk about Lorentz series, but let's talk about the Neumann series only here. So assuming that our matrix, square matrix F, has norm less than 1, that could be the spectral norm, but it can also any other matrix P norm. Then we know that the identity minus F is invertible, and we have this expression for the inverse of I minus F, the sum, infinite sum, or the series of F to the power K, geometric series. So this is now, look at it, applicable here in case S is close enough to S0. Yeah? If S is close enough to S0, this term here will be in norm smaller than 1, no matter what the norm of A0 tilde is. Yeah? You can, if you get closer and closer and closer, at some point you drop below the norm of 1. So in order to get the signs right, you have to write it in this way, then interpret this matrix as F, and then we apply the Neumann lemma. Actually, we are in the Jean-Golub summer school. Neumann lemma is very, very important in Jean-Golub's and Charlie van Loon's book. So if you start reading it, it's very, very in the beginning you'll find it. And what we get out after we have now applied the formula is this infinite series where we have everything power taken to the power of k, and the c and the b tilde are outside. And now we can pull the c and the b tilde inside. S minus s 0k and minus 1 to the k are only scalars, so the matrices of course commute with the scalars. So what we get here is then minus 1 to the k, c times a tilde k, b tilde, and these guys we abbreviate as mk. So what we now have is a power series expansion of the transfer function around or about S0. Okay, now the idea of approximation is to have a reduced order model that matches the first, say, L of these coefficients of this series. And as our transfer function is rational and our approximation is also rational, that's a rational approximation problem which can be solved by Padé approximation. But we'll come to that in a minute. I just wanted to mention that these guys for S0 to equal are called moments. And if you choose S0 equal to infinity, and then you have an issue with E. For simplicity, set E equal to identity in that case, then they are called Markov parameters. Because if you want to do this expansion at infinity and you have E is singular, then infinity is an eigenvalue of the pencil. So our original assumption wouldn't apply here. You can still do it, but it's a little more tricky. Because you basically then need an inverse of E, but E is not invertible. And you can still do it with a special generalized inverse, which is not the Moore-Penrose inverse. That's beyond scope of the course. Okay, I think Markov parameters and moments are also important in the exercises. So let's just write them down here for the case E equal to IN. Moments are minus C A to the minus 1 power k plus 1 B, and Markov parameters minus C to the A k minus 1 B for k greater 1. And M0 is taken as 0. Okay, so the Markov parameters are actually related to the Laurent series of the transfer function. So they will show up also in the exercises in some point, or you have to use them. And with these quantities, you can completely describe your transfer function, yeah? Because in the power series expansion, if they are all the same, your transfer functions are the same. Just as a hint. Okay, so this is why the method that we come up with is also called moment matching, because we try to match as many moments as possible. And in case of in case of matching Markov parameters, the problem is also called partial realization. So what can we do with a rational function of degree r, that means of denominator polynomial of degree at most r? We can match as many as the first 2r moments starting counting from m0. And this approximant is then the r per day approximant of the transfer function. I guess Marlis talked about that last week. Some. Yeah. So I will not get into that because it's not so important for us here. It's the most you can do. We will see in the next slide why. So that's the best you can do with a rational function of degree r. And this 2r has to be understood. It's true in this way only if this is a scalar function. If we have multiple inputs, multiple outputs, the number here, well, is different. We'll see later. Okay, how can we solve this problem? So how can we come up now with a reduced order model that matches these 2r moments from 0 to 2r minus 1? And of course, before we get there, it's clear our initial series expansion is only valid in the vicinity of S0, right? So S is close to S0, so this term here will be very small taken to the 2th power. Say it's smaller than 1 at least. Now you would argue that, okay, what the heck? Now I have approximated around a single point, but I want to have approximation on the whole imaginary axis. It's not true in all applications. This method was mostly used in the 90s in microelectronics, where you have a clearly defined operating frequency of your circuit. So you would choose S0 as the operating frequency of your circuit, and you only need good behavior close to that. And then there is a second argument that kicks in. G of S is an analytic function in the right half plane. Analytic functions, as you probably know from, or if you took complex analysis, are completely defined by their derivatives. So at the single point, at any given point in the complex, in the area of analyticity. And we match many of them here. If R is, say, 20, we match the first 39 derivatives. And the function has to be really wild to deviate then, even on a larger interval, not only close to S0, if you match its first 39 derivatives. So there are two arguments here. You have two motivations. Close approximation is important, or approximation close to an operating frequency is important in some applications. And also, because of this analyticity argument, you do better than this expression here tells you, often. Okay, so how can we solve the problem? And this is just a little bit of history. Please don't do that. Only if you have a system of order 3 that you want to reduce to order 2, you can do it. But it was the first suggestion by Pillage and Rohrer in 1990. There are certainly much older solutions to the Padé approximation problem. But this was the where the model reduction in microelectronics got started with. Therefore, I cite this paper. So assume the scalar case, and for simplicity, S0 equal to 0. So we are in this situation. Actually, if S0 is not 0, the methods are still called moment matching, and the M's are sometimes called shifted moments, and because we are usually lazy, we also sometimes only say moments in that case. But here we assume S0 equal to 0. So our reduced order transfer function should be a polynomial, a rational function of degree at most r. So you have a enumerator polynomial of degree r and a denominator polynomial of degree r minus 1 at most. That gives you the coefficients alpha and beta as free variables. And there are r in the enumerator and r in the denominator plus a scaling factor. The scaling factor cannot be used to give you more quality. So if you introduce a beta 0 here, it would only change the scaling of the alphas and the betas. So now what you want is you want that rational function to match the first r moments of the transfer function of the original one. So what you then do is you multiply through with the denominator and then compare coefficients, and you choose your coefficients so that the first two r terms with the up to the power s to the 2r minus 1 disappear. And if you write that down, these conditions, you end up with that linear system of equations. And that linear system of equations, if you take that you get from the conditions for the powers 2r minus 1 down to s to the r, or for the coefficients of s to the r to 2r minus 1, you get these equations. Because on the left-hand side, you only have powers less than r. So for these conditions, the left-hand side is 0. So the alphas do not show up in this linear system of equations. This is a Hankel matrix. It's symmetric over the anti-diagonal. And then the entries of the anti-diagonals are equal. If your system is controllable and observable, you can also prove that this is invertible. Or at least if you can prove that this is invertible if your controllability subspace and your observability subspaces have dimension larger than our observability subspace is not good term because you cannot really define it. But the number of observable states is larger than r, then this is invertible. That you find in system theory textbooks. So you can solve that linear system of equations for the betas, and then the other conditions that you get for the terms s to the power r minus 1 down to s to the power 0 give you then the expressions for the alphas. So you can compute these. So this is bad for many reasons. It's numerically completely unstable. Inverting Hankel matrices is a tricky issue. There are fast algorithms which are really unstable. You can do standard robust algorithms which then get very slow. But still, what you get are these polynomials. What you want is a state space realization. And going via the coefficients of the polynomials is a very bad thing to do numerically, because these coefficients are really sensitive with respect to round-off errors. So people realized that applying this wouldn't work in practice. And then people observed a connection, which then came known as the Padé-Lanczos connection, or I think I don't have all the references in here. I think there was a paper by Beresford-Palette in the 80s which made that connection. But in the context of model reduction, it was first used in these two papers by Roland Freund and Feldman and Paul van Doren and co-authors, both in '94. And they used what we already knew about this projection and interpolation connection. And here's the full theorem, which you will prove to some extent tomorrow, I guess, in the exercises. If we, because I use these abbreviations for these creatures that I just defined, if we put them in the projection subspaces, we get Hermite interpolation up to order 2k minus 1 in the single input, single output case, and to a different strange number in the multi-input, multi-output case. So it's in the multi-input, multi-output case, it's a little bit more complicated to show how many moments you really match. But the smaller m and the smaller q, the more moments you match. So this is the lower Gauss bracket. So if, say, you go up here to k equal to 10 and you have m equal to 2, you come up with 5, and q is equal to 4, and it's 2. You only match 7 moments in that case, while in the single input, single output case, you would match 20. So this was known for some years. There's a paper by Willemans Skelton which has this, at least in disguise. Grimme wrote it down in his PhD thesis and made the relations clear. But before that, they had already the paper, and also these other guys had this paper. So now we have this, we see this. We know what these guys are. These are just Krylov subspaces, right? So we can achieve the same as with this asymptotic waveform evaluation algorithm, namely the matching of the moments by using projection-based model reduction with these Krylov subspaces as the subspaces to choose from. And this is then what is the Padé via Lanczos method, or at least Roland Freund called it that way. And you just have to remember that the moments and the derivatives of the transfer function, here we have matching of the derivatives, here we had matching of the moments, but that's the same because they are just scaled variants of each other. That you can do that via the Lanczos process. So you need to project onto these two subspaces, and that would be, for instance, a subspace that you could compute with the Arnoldi iteration. That would be another Krylov subspace for which you could compute the basis with the Arnoldi iteration, and then you could use it in that way. But Roland Freund also made the observation that if you use the unsymmetric Lanczos process with B tilde and C tilde as starting vectors, the unsymmetric Lanczos process does compute the reduced order model with that property as a byproduct, so you don't have to do the projection explicitly. Yeah, let me just remind you, if you haven't seen it. Unsymmetric Lanczos. computes, if you have a matrix A, it computes two bases, Vk, Tk, plus, say, Rk plus 1. So this is a typical, in the symmetric case, that would be the Lanczos recursion. But now Tk is no longer symmetric because A is possibly not symmetric. So you compute a second relation. Plus Tk plus 1. So with a second set of residual vectors. Tk is a tridiagonal matrix with which is non-symmetric, and you do it in the typical Lanczos or Arnoldi fashion. You can derive the algorithm by comparing columns one by one in these two equations and then write down the equations to derive the algorithm. And what you build up here is the projection subspace V, this one. If you choose, say in the single input, single output case, V1 equal to tilde B, and W1 equal to tilde C, or maybe W tilde. You have probably to apply scaling to ensure the orthogonality. So there's another thing that we have here is WK transpose VK is equal to the, can you see that? No. It's equal to the identity. So this is the biorthogonality condition that is driving the iteration. In any case, in that situation, the W1 then becomes just a version of C tilde that satisfies this condition. You have that as the starting vectors in your subspaces, so you see that you construct V in this way and you construct W in this way. Let's give that a tilde. Then it's directly related to this. And your reduced order model is Tk will become your A hat. And there are also explicit formulas for B hat, and C hat, and unfortunately I forgot to note it down. Anyway, B hat and C hat are also a byproduct of the algorithm. Yeah, so you don't have to do the projection explicitly, you get it for free. That has some disadvantages. It uses the unsymmetric Lanczos process to begin with. The unsymmetric Lanczos process, if you have learned about it or if you have studied Golub van Loon, you know that it's a very difficult to use method because it has breakdown, and it means breakdown in the way of a serious breakdown. So you can have quantities to divide by in the course of the algorithm which become zero without that you stop with a converged deflating subspace or with any information. You can deal with that, and Roland Freund was the guy to deal with that. You can extend it also to the multi-input, multi-output case using a so-called band Lanczos process. But in that form, it's rarely used nowadays. You can also, using the projection framework, and ignore the W space. You just use that space that you now compute in a numerically stable way using the Arnoldi process. And then for the projection, for the model order reduction, choose W equal to V. That gives you the so-called prima method. Passive reduced interconnect macro modeling algorithm, I think, was the abbreviation. That came up in 1997. And as it uses one-sided projection, you have less freedom in the projection, so you get only matching of the first R moments. So two-sided gives you two R moments, one-sided gives you R moments. It has the advantage that it preserves symmetry, in particular in these circuit models that people were working on in the 90s. So this is history. There are a list of properties of this process. It doesn't give you any computable error bounds for the L2 norm in the output. There are now efforts to do that. There is a local error bound actually by our host, by Sajun Bai. But they are not really helpful in assessing the overall error. And the ones that we can compute nowadays give you more information, but they're still often very pessimistic. We still, unless your application tells you where to put your S0, we don't know where to put it. There is particular for second order systems with only one damper, you can do something. Serkan Gugershin and Chris Beatty published a paper on where to put your evaluation, your interpolation point. And usually you get only local good approximation. As I told you, it's better than you expect because of this analyticity argument, but still at some point your transfer functions will deviate if you only expand your transfer function about 1 point. So what people then soon enough discover that it's a good idea to maybe expand on several points, and we'll come to that in a minute. And the preservation of physical properties like stability, that's a tricky issue. The two-sided version that is based on the unsymmetric Lanczos process, that would usually not give you a stable reduced order model even if you start with a stable one. So you have to do extra steps to remove the unstable poles that are spurious in your reduced order model. And that usually destroys the moment matching property to some extent. So it's always a trade-off. There's no free lunch here. Unless your system A is symmetric, then of course if you do one-sided, you preserve stability. And there's a more general concept of dissipativity where it's also true, and we will do that in the exercises. So let's change the perspective a little bit. This is just a repetition. Now we come to the issue, okay, one expansion point might not be enough. Let's select some, but where? Where do we put that? So this is just a repetition on how we compute the reduced order model by projection, and that's a repetition of what we have just seen. Moment matching gives you these conditions if you choose, say, k different expansion points with a different number of moments that you match in each point. So it would be achievable if you run this two-sided Lanczos process, Pade via Lanczos, or the Arnoldi process, or whatever, in several expansion points, and then you concatenate all these bases that you compute to one basis, project, get a reduced order model. That you can achieve. But still, the question is where to put these expansion points Sj. And for what will follow, we only use, let me just give you one formula before we get there, because that's also sometimes quite helpful. There is actually an error expression that is not too helpful, but it gives you an idea what you could do. It's in that form true for the CISO case, but you can also do it, I think. So in the H2 norm of the error can be written in the following form. I hope I get it right. And I will explain it in a second. Correct? Okay. So what do we see? That's the H2 error in our reduced order model. That's a general formula. If G has poles lambda j and G hat has poles lambda j hat, our reduced order model is of order R, so we have R of these lambda j hats, and our full model is of order N, so it has N poles lambda j. So you can always express the H2 norm of the error as the sum over the difference in the poles of the original model mirrored or reflected at the origin. So if you have a pole, say, here, this expression evaluates the transfer functions here. And the same for the reduced order model.
Should it be as G instead of G hat in the second one?
Oh yes, thank you. Ich aufgepasst. Yeah.
Absolute values. But are not absolute values.
Doesn't matter too much. I have to look it up.
Without the squared. So it's really
Yeah.
the residues. No, there's the squared effect, but then that's really just the bracket. So that's just the constant.
I mean that these are not absolute values?
Exactly.
Oh, okay.
Now you have the G hat either switch with the G in the second part or you put a minus. So the second part is either a minus for before the sum or it's reversed in the bracket in the second one. So it's
Okay. Yeah. Well, it doesn't matter. Then it's not correct in Antula's book. Okay. Because he had a plus there. The exact form of this formula you don't need to memorize. What is important here is the idea that what can you do with that formula? And with the idea of interpolation, you can make some of these guys to 0. In particular, you can take those, for instance, for which the RKs are large, and by choosing your reduced order model to interpolate in either this mirrored poles of the original system or the reduced order model, you can make some of these guys to 0. And depending on the signs and the values of RK and RK hat, you could choose. And if you read the book of Antula's, 2005, he suggests to take some of these poles of the original system to zero out some of these terms here. Those that have the biggest contribution to this H2 error. And that would give you an idea on how to choose to select these points here in the in that formula. But it turned out that a better idea was to use the second half and to make that part completely zero. And that's what we'll talk about in the rest of this lecture today. The problem is, of course, you don't know when you start computing your reduced order model, you don't know its poles. So you could say, okay, I want these poles of the reduced order model, but then if you want to have interpolation, you do this projection, the reduced order model will not have these points as poles. Yeah? You do the projection, but the reduced order model, the poles are not related. You only have this interpolation condition. Okay, so here's that simplified version that we will use now, because we'll only use now Hermite interpolation up to degree 1. And the algorithm that I'm heading to is this iterative rational Krylov algorithm, which now aims at selecting the poles Sj, j equal 1 to k, so that this is minimized. And once they had this formula, somehow they rang a bell that there was something already known about what are the necessary conditions that a reduced order model has to satisfy, or a transfer function of degree r that is a best approximation to G in the H2 norm. And that is long known from approximation theory from the 20s and 30s of the last century. And these conditions are actually something that you will see here will make zero these terms, right? The necessary conditions are that you have interpolation at minus mu I, where mu I are the poles of the reduced transfer function again. These mu i's are, maybe I should put that here to make the notation easier for you. That we have the complex conjugation here doesn't matter, because if we assume for the moment that we have a real model and a real reduced model, the poles come in conjugate pairs. So it's the same as this expression. So if you have this condition up here, you would zero out this part of the error formula, right? And then you also have part of the necessary conditions is that the derivatives match. So you have Hermite interpolation. And now going back to this theorem, to simplified version, it's clear what to do. Yeah, this gives you exactly these two conditions, interpolation at the point and interpolation of its first derivative. You just have to put that creature into the subspace and that creature. So the only thing you have to do, you have to know the poles of the reduced order model and compute these particular subspaces. Now comes a little bit a tricky issue. In the multi-input, multi-output case, these necessary conditions are no longer related to moment matching. In the CISO case, it's the same as moment matching about mu I. If you have more than one input, more than one output, that's no longer true. The conditions are relaxed. They look more complicated, but they are actually a relaxation to moment matching. You have interpolation only in certain directions. So in the MIMO case, G and G hat are matrices, Q times M matrices. So you don't need interpolation of the full matrix, so no matrix interpolation. You only need interpolation in certain directions. And these directions are also related to the poles of the reduced order model in the way that the directions are determined via the eigenvectors of the reduced state matrix. So these are the necessary conditions in the MIMO case. There are more than two now because you have one direction, right direction, one left direction, and for the Hermite part you have a bidirectional tangential interpolation condition. So this is called tangential interpolation. Okay, now the question is, what can we do with this? As I said, we don't know. In order to evaluate these conditions, we would need to know B hat, C hat, and A hat, and its eigenvalues and the eigenvectors, but we don't know the reduced order model before we compute it. So it's in German we call it an egg-hen problem. What was first, egg or hen? What is first, reduced order model or the poles? So what we can do is, of course, we can enforce these conditions at locations mu I by the projection framework that gives you interpolation, as explained numerous times by now. But again, if I now project with these subspaces, the reduced order model will not have poles at mu1, mu2, mu r. But you can show that if you do that, you go basically into the direction of the gradient of your error function. And that gives you an iterative procedure, so you repeat that. You do that once, you project, compute the new poles of the reduced order model, then replace these mu1 through mu r by the new poles, compute new v and w, project again, and if you're lucky, that algorithm converges to a stationary point where at the end the reduced order model really has mu1 through mu r as the poles. And that's the iterative rational Krylov algorithm called IRCA that was first suggested by Serkan Gökçin, Chris Beatty, and Tanos Antoulas. And then there was a competition on who did the multi-input, multi-output version first. There was a paper again by Van Doren and Grimmer and Absil about that. They had a paper on tangential interpolation already years before this IRCA algorithm came up, but they didn't know which interpolation points and which directions to choose. They just gave the framework for tangential interpolation. But then, of course, when they came up with the first IRCA version for the single input, single output case, they immediately knew where to put that, so they published the MIMO case. The MIMO case then also found its way into that paper as a remark, and Bunse Gerstner and student also derived the version for discrete time systems. That's another issue. Okay, and here's the algorithm. So, questions? It looks a little complicated. It's given here in the MIMO version. Do we use the MIMO version in the implementation or only thing? No. So in the afternoon, you're going to implement that, but only in the single output, single input case. So you don't have to worry about these directions here. All these tilde quantities go away. So the stopping criterion is the critical thing. So you stop based on convergence of the pole set of your reduced order model. So you start out with some selection, maybe a random choice, whatever, of poles. good idea is probably, if you know something about your problem, to choose them in related to the frequency range that you are interested. If you want to have a real model, you better make this set of poles, the starting set of poles mu1 through mu_r, closed under complex conjugation. Otherwise, you will have definitely a complex reduced model. You can work with that as well, but people in applications are often not so happy with complex models. Then well, I think in the ZISO case, you just need to select the initial poles and you can go. In the MIMO case, you have actually to select the reduced order model and compute its poles and so on. But you can, of course, choose a diagonal matrix with poles. And then, so this step is only necessary in the MIMO case. And then you compute your subspaces. In the ZISO case, these are rational Krylov subspaces, but for implementation purposes, one is often lazy and only computes the solution of these linear systems of equations and then orthogonalizes the whole space, as is done here. So you could compute it basically in the ZISO case, at least by what is called the rational Krylov algorithm, but nobody does that actually in practice. Then here you have this normalization factor that you need. In that form, V times W transpose will not be a projector. Yeah? So only if you insert that case in front of the W, you will have, or actually you have to transpose it, and then it's getting the, if you would set W equal to, after this step, W equal to W times V star W inverse, then you would have this property that V times W transpose is a projector. Here it's worked into the, and actually I think I switched notation. I usually used, for transposition and complex conjugation, I usually used on previous slides H, and here it's H star. Unfortunately, in the moment matching section, I used H star to define a matrix that in the start didn't have anything to do with complex conjugation, so there's a little bit of confusion here again. Okay, yeah, that is the mathematically most advanced algorithm in that area right now. Since it came up, there was a lot of effort to make moment matching methods competitive in the way of giving as accurate models as this one. So there is now a selection of papers that try in this moment matching framework, without having this H2 optimality conditions in mind, choosing the interpolation points as J, at which you match moments also in a way that certain more or less heuristic error indicators are minimized. And you get very good methods that are often more practical than that one. It has issues. There's no guarantee that it converges, in general at least. There are, under symmetry conditions, you can prove convergence to a local optimum. There is no guarantee that you have global optimality. In practice, it often does, but it's not, as far as I know, it's not shown anywhere that you get to a global optimum. Sometimes it has difficulties to converge to begin with. In particular, in the multi-input, multi-output case, things get quite fishy. So these moment matching methods that are enhanced by selection criteria for the expansion points based on heuristical or practical error bounds, together with possible adaptive choice of the number of moments to be matched in each point. So here we only match the first derivative, the first moment, so to speak, and only in tangential directions in the multi-input, multi-output case. But you could also go higher and adapt that order also at the various interpolation points, and that gives quite practical methods because they're usually easier to compute than these algorithms. You need to solve quite a few number of systems here. So if you have, say, 10 poles, it's 20 systems to be solved. There are relations among them that you can exploit, but 20 systems, and you need maybe 20 iterations, so you have 400 linear systems to be solved. And in this moment matching area, you often get away with only solving 10 linear systems. So your reduced order model will not have the optimality properties than this one, but it might still be good, and it's often much faster to compute. So it's a matter on what you want, which algorithm to choose. Okay, so that was a little bit of philosophy about these two things. Moment matching, tangential interpolation, two sides of the same medal. Basically, it's all rational interpolation. Techniques are the same. Numerical computation of the reduced order models requires solving linear systems to compute bases of certain Krylov subspaces. These subspaces are used for projection to achieve at a reduced order model. So this is, in a nutshell, what all these methods are about. And with that, I'd like to close for today, because now we would have to start a completely new area of model reduction methods, but we'll come to that tomorrow. I just would like to mention that tomorrow in the afternoon there's this research seminar, and the talk will be actually about such a moment matching method with certain adaptivity strategies for selecting interpolation points and the number of moments to be matched. And yeah, just as a teaser for tomorrow.